shifting gears back to algebra. The first part of this algebra book that we're looking through, so this is the OpenStax Elementary Algebra, so this is 8th grade algebra. And it talks in the initial part about the number system that we have. And so if we quickly review the types of numbers that exist out there, you have the natural numbers, which is given by this, that's supposed to be the letter N. The natural numbers, which is everything usually given as 1, 2, and so forth, up to infinity. Then you have the integers, which is the one that I use most often, well, in terms of like when we're talking about sets of numbers. So the integers are all the numbers 1 to infinity and the negative numbers and the number 0. And this was actually the introduction of the 0 to the numbering system was a huge, huge change in the technology of mathematics. This made numbering, it made doing math or calculations, or so it made arithmetic significantly easier once you have the 0, because then you can use the 0 as a placeholder and you can do the kinds of additions and subtractions and multiplications, kind of mathematical operations that we do now are greatly simplified by adding the zeros and the negative numbers to this list. Okay, so the natural numbers are basically the ones you count with. Very few people really talk about the natural numbers if they don't have to. The integers are a very common one. And then there are other types of numbers that you have to construct for a variety of reasons. One of them is the rational numbers, Q for quotient. So this is all the fractions. The number of fractions is equal to the number of natural numbers. So the number of integers is equal to the number of natural numbers. The number of fractions is also equal to the natural numbers. So all of these things, these three sets of numbers, are equal to each other in terms of the number of elements that they have. And the way that you can show that these things are equal to each other is you basically say, is there a number here? If I can come up with some counting scheme or some enumerating scheme or ordering scheme, is there a number in the integers that I would not be able to reach after a period of time? Like I would run out of natural numbers before I reach it. And the answer is no. So you can pick any number you want, like Avogadro's number, 6 times 10 to the 23. And if you start your ordering scheme, then you can arrive at 6 times 10 to the 23 before you run out of natural numbers. The ordering scheme you have to do to make sure that you actually hit everything is that you would start at 0 and then you go like 1 and then minus 1, and then 2 and then minus 2 and then 3 and then minus 3. So it might take you twice as long. You'll have to count to 12 times 10 to the 12 times 10 to the 23 before you actually arrive at this number. But you will get there, and there's still an infinite number of things into the distant future. So the same thing is true with the rational numbers, Q. So for example, you can pick any fraction. You need to just come up with an ordering scheme and you'll get to any fraction that you want. The way that this is usually shown, at least the way that I learned it, a little bit differently. What do? You go 1, 2, 3, 4, 5, 6, and then you go 1/2, 1, or no, you go 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, 1 over 6, and you go 2 over 1, 2 over 2, 2 over 3. You come up with some structure that looks like this. 1. Okay, so these, and then that's a half, and then this is 2 2/3, and then 3 over 1, 3 over 2. You work it out like this. You write them all down. I don't remember the exact order, but then you count along these diagonals, and no matter what fraction you choose, eventually you will get to that fraction. And you can do the same thing if you want to include the negatives. Then you work your way. You add the negatives over here, and then you just do that diagonal on this one, then that diagonal on that one, and that one diagonal on that one. And so any rational number that you want to find, you can arrive at it before you run out of integers. Therefore, they're the same size. These are all called countably infinite, this type of number. There are also other numbers that are going to be important, such as the reals. So this is basically all the numbers. Given the fact that there are rational numbers, there are also irrational numbers, which I don't recall what symbol the irrational numbers are. If they have, does irrational numbers have a symbol? I don't recall if they ever have a symbol or not. But there are numbers that you cannot express as ratios. For example, the square root of 2 is the one that most people bring around. This is a number that you cannot represent as a fraction. You can approximate it with a fraction, but you cannot make it identical to a fraction. This is the complex numbers, I believe. And so I don't think that, so that's not quite the irrational numbers. This is a separate set. There's other sets that are called algebraic numbers. The square root of 2 is an algebraic number, where like pi, for example, is not an algebraic number. An algebraic number is a number that can be the solution to a polynomial equation, which we'll get to in the series of streams. Any number that is a solution to a polynomial equation with integer coefficients is called an algebraic number, because you can get to it with algebra. And so the square root of 2 is an algebraic number. Pi is not an algebraic number. It is not the solution to any polynomial equation with integer coefficients. R is real. This is real. So the real numbers is basically all the numbers that don't include the number I, which is the square root of -1. So the real numbers is definitely larger than the integers. Real numbers, there are more real numbers than there are natural numbers. So the natural numbers are countable, the integers are countable, the real numbers are not countable. You cannot write them all down and get to any real number that you want. Any small subset of real numbers has more numbers in it than all the natural numbers, all of the rational numbers, all these things combined. They do not add up to any minuscule portion of the real number line. And there are ways to prove this, a variety of ways to prove this. One of them is to say, okay, let's pretend that we can actually enumerate all the real numbers. One of the ways to do it would be to say, okay, I'm going to write them all down. So I'm going to just list all the real numbers that exist between 0 and 1. So I get 0.001, and I write them down in some order, and 0. Blah, 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 and I write all these numbers down, and then I write this one down, written as a decimal. So all these are not numbers 2. These are not the number 2. They're just a bunch of numerals. And then what you do is you say, okay, I claim that this list is complete, that it has all the numbers between 0 and 1 listed. And then someone comes along and says, actually, you missed one. I'm going to take this number, and whatever number is here, I'm going to construct a number that looks like this. It starts with a 0.5, and it could be any number. You could put any numeral there. It could be 0.4 or whatever. And I'm going to go down the diagonal, down this diagonal, and I'm going to keep writing 0.5 unless this number here is a 0.5 or is a 5. If that number is a 5, then I'm going to write a 4 instead. And I'm going to keep going down. So I'm going to get 5, 5, and then 4, and then 4, and then a bunch of 5s, stuff like this. And now I've constructed a number that lives between 0 and 1 that is different from all the numbers that I claimed was in the initial list. It's different from all of these things in at least one place. There's at least one location where this number is different than all these. Therefore, I've made a number that's in that interval that you missed in the list where you claimed that it was all the numbers. So this is an example. I think this was Cauchy that proved this. An example that shows that the real numbers are uncountable. Okay, so we have the real numbers, we have the rational numbers, we have the, there it is. The complex numbers. What's the complex numbers? Is that C? I think that's the complex numbers. Well, my mouse thing is not showing up very well. Complex numbers like this. So that's ones where you include the square root of -1. So that would be like a plus bi, these kinds of numbers. And we will get to those as well as we go through this unit of material. All right, so we have the numbers. Now, what we talked about with, what does algebra mean? What are we talking about when we're doing algebra? Oh, let me revisit very quickly the idea that when we have numbers, the use of numerals is really useful for doing mathematics. So the use of numerals meaning that you have like 531, something like this, and each of these numerals represents something. So, okay, so when you have these numerals, so like 531, the fact that this represents something, this represents the ones digit, and this represents 10 of these. So every time you roll over on this, you increment this counter. And then every time this one rolls over, you increment that counter. So this is going to represent 100. You enumerate up to, in this case, 500, means that this is turned over. this one is turned over enough times to increment this one to the point where it turns over enough times to increment this one. You do that. It takes 100 increments to turn this one over once. And so that represents 100 of these things turning over. And then writing them down in this fashion, the existence of a 0 allows you to have something like 302. In the absence of a 0, how do you write down this number? You can't do it like with Roman numerals. We've talked about, mentioned that before, that like M, X, L, D, I, or whatever. This is not something that has a 0 in it, and therefore the way that you enumerate things becomes really clunky, and the way that you do calculations with them becomes really, really clunky. So that is, invention of the 0 is important because it allows us to write numbers in a pretty compact way. You can have, we mentioned that you can do a different base. So right now we're using base 10. Most of our stuff is in base 10, which means that there are 10 numerals that we can use, 0 through 9. We mentioned that you can do hexadecimal, and I said it right this time instead of hexagesimal. Hexadecimal is a base 16. So then there are 16 numerals. Those go from 0 to 9 and then A to F. Okay, and so there's if you count these up, there are 16 of them. So you increment all the way up to 16, and then you roll over, and then that gets you. So if you have F is equal to 15, and then if you go 10, like 1 0 in hexadecimal is actually 16. And then this would be 17, 18, and so forth, because this represents the number of 16s that you've had instead of the number of 10s that you've had. So hexadecimal, people use binary. So binary would be base 2, where you only have 0 and 1. You have 2 numerals. Octal is often used as well, but it's a little goofy. So you go up 0 through 7, and then it rolls over. There are a number of other different bases that you can count. The important thing is that all of the numbers in any base can be rewritten in any other base. So you can start with base 2 and have like 1 1 1 0 in base 2, and that corresponds to no 1s, 1 2, 1 4, and 1 8. So this is going to be an 8, a 4, a 2, and a 0, and you add all these things up because that's what they represent, is how many times you've done the increment in the past. You add all those up and you're going to get what, 14? So you can map from any base to any other base 1 to 1. It's just another representation of the integers. How do you keep track of the integers? An important thing to note is that the Babylonians had a base 60 system. So they had 60 different numerals that they used, or 60 different symbols that they used to count, and then it would roll over. So this is part of the reason that we have 360 degrees and 60 minutes and 60 seconds. Goes all the way back to the Babylonians and their numbering system. So the concept of 0 existed before. People knew what nothing was, but they didn't have a symbol to represent it, and they didn't have a way to incorporate it into their digits the way that we do now. So thank you to the Indians for bringing that to us. I've heard that base 12 is a really efficient base. Any idea why? So I believe that base 12 might be really efficient for a few reasons. One of them is that it has a lot of divisors. So 12 can be broken down into 2 times 2 times 3, right? Is that right? That's 12. And so that means that it's divisible by 1, 2, 3, 4, 6. 1, 2, 3, 4, and 6. And so that's a lot of divisors that go into 12. So it's really easy to break it down. That might be one of the reasons why it's really divisible. So 60 is another one that does that. 72 is pretty good. Some of those things. Now, let me give you an example of what changing bases can do for you and your health. So one of the things I mentioned before is that the real numbers is uncountably infinite. You can't list all the real numbers. So let's do something real quick. Let's take the real number line. Now this is actually not algebra, this is real analysis, but we're going to do it anyways because we're talking about bases. Okay, here's the real number line. And I'm going to do a ternary expansion. So we're going to look at the base 3 division of the real number line. So that's going to divide the real number line into thirds. So if we look at the decimal expansion, this starts at 0 and it goes to 1. If we look at this is a 1. We look at the decimal expansion of this in base 3. So we write it as fractions. This is going to be 0.0. It's going to start as 0.0. And then this is going to start as 0.1. And then this part's going to start as 0.2. Does everybody believe that? So we're talking about base 3, so we can only go 0, 1s, and 2s. And then it rolls over back into, so base 3 is going to mean you've got 0, 1, 2, and then that's 3. This is what 3 looks like. And then 4 would look like this, 5 would look like that, and then 6 would be 2 3s. So we're talking base 3 here. And if you do the decimal expansion, then this part here, that decimal is going to start, even though it looks like a smiley face, it's actually 0.0. And this is going to start as 0.1. And every number that lives in this third is going to start with 0.1. Every number that lives in this third is going to start with 0.2. Now I'm going to take all these thirds and I'm going to remove this one. I'm going to remove this third right here. So this is completely removed except for the endpoints. I keep the endpoints back and I remove this one. All right, now with what's left over, I'm going to divide that into thirds. So here's a part that's left over like this, and I'm going to divide it into thirds. And there's a part left over here as well, and I'm going to divide it into thirds. So this part, I bring those down. And if I look at the decimal expansion in base 3 of these things as well, I'm going to get 0.00. This is going to be 0.001, and this is going to be 0.02. This one is going to be 0.20, 21, and this is going to be 0.22. And if I remove the middle thirds, then that's getting rid of this piece right here. So I get rid of that, and I do the same thing here. I get rid of this. Okay, and what I'm going to do is I'm going to start stacking up these pieces. So I stack up that first piece that I removed. I stack up these 2 pieces here that I've removed. So they look like this. And I keep doing that. So now I take the middle third of this piece, and I stack those up. I'm going to get some of those. I'm going to get 4 of them. And I keep stacking them up. And what I'm doing is, in this ternary expansion, I'm removing anything that has a 1 in it. Any of these numbers that has a 1 in it gets pulled out. And all I have left over are things that start with 0, that have 0s and 2s in it. So all the endpoints that are left over after this have 0s and 2s. Okay, so the question that I have is, you start with this whole interval from 0 to 1. How much do all these pieces that I pull out add up to? What is their final length if I stack them end to end? The answer to that is, these things all together have a length equal to 1. Because I've only removed individual points, and points have no size. Okay, so then the next question is, so I've done this, I've taken away everything that has a 1 in it in this ternary expansion, and now I've got something that's equal in length to what I started with. The question I have is, how many numbers are left over? The number of numbers that I have left over is all of them. And here's how you can tell. So I can write down any number that I want as some decimal, some binary number, 0, 1, 0, 0, 1. So now I'm working in base 2. I've got 0, 0, 1, 1, 1, 0, 0, whatever. So I write this all down. And this is going to represent some real number. This goes on forever. It's some infinitely long decimal, but it's written in base 2, so I only have 0s and 1s. And there's a map between all these numbers. So I can get any number between 0 and 1, I can write as an infinite decimal using 0s and 1s, like doing it in binary. If I take this number, I can recreate this number just by replacing 0 goes to 0, but 1 goes to 2. And now I can find that in all the endpoints that I had left over. Because remember, we pulled out from the initial number line any number that had a 0.1 in it, which means that all the numbers that are left over have 0s and 2s in them. All the numbers that are left over when I remove all these thirds have only 0s and 2s in them. All the 1s have been removed. And now I'm saying that any combination of 0s and 2s corresponds to some number, 0s, that I can make out of 0s and 1s in binary. It's basically just rewriting everything with 0s and 2s instead of with 0s and 1s. You have 2 different numerals instead of 0 and 1, which means that every number that I started with, I have a map to it with what I ended with. So I start with a unit interval. I remove virtually everything out of that unit interval, like this, and I have the same numbers left over at the end than what I started with. So that's kind of cool. All right, so this is an example of weird things that you can do changing from one base to another. So this is called, is it Cauchy? No, it's the Canter Set. The Canter Set. And I think that people didn't really like what he did, and so he was very sad, and I think he eventually killed himself. So, but the Canter Set is a nowhere dense set. And there's all sorts of weird things you can do with the Canter Set. For example, there's a thing called the Devil's Staircase. Let's see, look that one up. Devil's Staircase. Other uses, the Canter function. Yeah, that's the Devil's Staircase right there. It has an infinite number of steps. It grows continuously from 0 to 1, but it has no, the derivative is 0. The slope is 0 everywhere. So every step is flat, but it's a smooth line that goes from 0 to 1. And you construct it using the Canter Set that I just showed how to make. Okay, so these are games that you can play with changing your base in the numbering system. And we use them all the time. In particular, hexadecimal and regular decimal we use all the time, and binary. Those are probably the three most common. So that when you have a set of numbers that you're working with, when you're talking about an algebra, you're talking about having an operation that you apply to those numbers. So for example, we start with the integers, and we're going to have an operation that we apply to the integers. It's a binary operation. Binary operation means that you take two elements out of the integers, you do this operation on them, and you get a third element also in those integers. So that means you can take 3, we do plus 5, and that gets you 8. So, and all of these things are integers, and I do that with this binary operation. I mentioned before that this is only an operation. You can only do it to two things at a time. You can't add 3 numbers at once. No matter how much you might try to do a 2 plus 3 plus 5 and magically have it all work at the same time, so this would get you to 10, you can't do it. You can only do it 2 at a time. You can only either add 2 plus 3 or 3 plus 5 or 2 plus 5 and then add the third number to it at the end. So a binary number or binary operation, when you take 2 elements out of the set and you will get a third element out of the set. So that's called a closed binary operation. If your closed binary operation and the set of numbers that it works on has the following properties, that is, it has a closed binary operation, which we've already established, so you have a plus in this case. You could also have a multiply, but that will require a small change. It's associative, which means that you can group it this way. 2 plus 3 is 5, plus 5 is 10, or you can group it this way. 3 plus 5 is 8, plus 2 is 10. So the fact that something is associative, that is also an if something contains that. You also have inverses, meaning that if you take, actually before I do inverses, I should do that you have an identity. That's one where you take any element out of here, like 7, plus the identity, which is 0 in this case, gives you 7 back. So the identity element is the element that when you do this operation on it returns what you started with. That's the identity. And then the last thing that you need is an inverse. So that says inverse. The inverse is the element, you take an element, there is another element in that set that will get you back to the identity. So in this case, it's the negative numbers. So the integers are this is called a group. The integers form a group with addition being the operation. So you have this operation and the integers are a group. They are associative. You add them together, you get a number. You can group them any way that you want. You may or may not be able to change the order. In the case of adding integers, you can change the order, but that's not always true. And then, you can always group them. You can always group them up 2 by 2. And so that's the associative property. There is an identity, it's the additive identity, and there are inverses. So this group structure actually corresponds to geometric shapes. So anything that you can form a group with, you can also have some geometric shape associated with it. And an example that you can look at is you can have a group on on 12 integers from 0 to 11. And you can have inverses and the associative property and stuff like that, which is telling time. So you can say like 8 plus 8 gives you, that would be 4. 8 plus 8 gives you 4 when you're looking at what's called Z12, which is the clock. The clock face is Z12. So 8 o'clock, 8 hours after 8 o'clock is going to be 4 o'clock. And that means that you can have like 8 plus 4, 8 plus 4 gives you 12, which is going to be 0 o'clock. And so you don't even need negative numbers in order to have an inverse. It can be whatever number gets you back to this identity. So when you're telling time, the inverses aren't the negative numbers. When you're telling time, the inverses is whatever 12 minus your element is. And because that will get you back to 0, which is like, you know, being back to the top of the clock. One property that may exist in a group but doesn't always exist is commutative. Okay, and that's the fact that you can have 3 plus 5 is equal to 5 plus 3. This is not always true with a group structure. So you can have a set of numbers where you have a binary operation, or you can have a set of some representation. It might be a Rubik's Cube or something like that. And you can have a binary operation on it. So you take two numbers, put them together, and you get a third one out. Or two actions and put them together and get a third action out. So this could be rotations in a three-dimensional space. You can rotate, for example, here's your three-dimensional space. You can rotate around this angle here. That's usually given by theta. If you're a physicist, if you're a mathematician, it's given by a different thing. And you can also rotate around this way with some angle phi. So rotations in 3 dimensions form a group. You can do any rotation, you can do any other set of rotations, and you'll end up with some third rotation in this 3-dimensional space. However, while these rotations are associative, you can do them in any pair that you want. Start here, now rotate. You can't do them in any order. If you do one rotation, so a rotation around one axis followed by a rotation around a different axis is not the same thing as doing them backwards. So that's an example of something that has the same properties, many of the same properties as addition, except that addition you can switch the order of things, and with these rotations you can't switch the order. All right, here is a question. If you draw two concentric circles, if you draw two concentric circles and a line segment from one center to the outside, you will always have equal number of points, but obviously the larger circle would have more points. But points have no size. You can always map one to the other. So was spoken here is you have two concentric circles and you draw a line basically like this. These lines always, for every point on this circle here, there's a corresponding point on the inner circle. They have the same number of points. There's no difference. There's a one-to-one map between points on the outer circle and points on the inner circle. Even though it looks bigger, it actually has the same number of points. Let's see, maybe different aspects of it talk about one way to interpret it is that's an asymmetric dimension different from our spatial dimensions are symmetric. I don't understand that comment, but it looks great. Let's see, am I a physicist or a mathematician? I am both a physicist and a mathematician, but mostly physicist. What makes the larger circle larger? Probably the nature of the map. You know, what it's mapping it from a mathematical space onto a coordinate system is what makes it larger. So how can you tell how big that circle is compared to this circle? They might be the same size. So I think it's us taking, here's this set of points, and I'm going to map it onto a coordinate system, and then you rescale the coordinate system is why one would be bigger than the other. All right, let's see. So we've covered the fact that we have a binary operation addition, and when we're working with the integers, we have it's associative, it's commutative. In the case of addition, it's commutative. It has inverses, and it has an identity. There are other operations that we have, and in particular, we're going to talk about another one, which is multiplication. Multiplication does not work on the integers. So this forms a group. Addition on the integers forms a group. Multiplication on the integers does not form a group. So what were the elements of a group? We have to have an identity, identity element, we have to have inverses, and we have to have associativity. Associative, that says associative. Okay, with multiplication, we get associative. So 3 times 5 times 2, it doesn't matter how we group it together. If we do 5 times 2 first and then times 3, or if we do 3 times 5 first and then times 2, it's associative. Multiplication is associative. We do have an identity. So 3 times 1 is going to be, is going to give us 3. And another way of doing this is 3 times 1 is 1 times 3. These have to be the same. That's one property of the identity, is that you have to be able to do it on either side. Is that actually true? I think it is true. We'll go with it. For multiplication, it's certainly true. But inverses, in the integers, there are no inverses. And so multiplication does not form a group. It doesn't have the same structure as addition over the integers. If we instead expand ourselves to the rational numbers, then we have the inverses. So the inverse of 3 is going to be a third. Okay, but this is not an integer. And so we have to expand to the rationals. In the rational numbers, multiplication forms a group. Okay, so 3 times a third is going to give us 1, and that is the multiplicative identity. Okay, so we have, if we're talking about at least the rational numbers, we have a group, because the rational numbers also form a group over addition. The fact that they're integers or rationals doesn't really matter to addition. You get the same things. But for multiplication, it does matter. So if we're talking about the rational numbers, we expand our set of numbers that we're working with. Both addition and multiplication form a group. So the next thing that what typically happens when we're working with math in terms of what we learned in elementary school is actually called a field. Okay, and in the case of both addition and multiplication, they are both commutative. So not only are they associative, they have their inverses, they have their identity elements, but they're also commutative. The commutative is a weirdness. That's not common to all of these mathematical structures. Some things that are groups are not commutative, as we've seen with the rotation. A field is one where you have a set of numbers. In this case, we can work with the rational numbers, and you have two operations, plus and times. They don't necessarily have to be plus and times. That could be, these could be different actions that you take. But when you have this with two different operations, and it's closed, and you have inverses, and it's commutative, and it's associative, then you get a field. And that's most of, like, the arithmetic that we learn with numbers, we're dealing with a field, which is a slightly more complex structure. Okay, so let's go back to this chapter. Now that we have the basics of our number system and how numbers operate, what other things do we need to learn about? Well, we know when we're dealing with numbers that we have, so now we have a way of showing what a number is. We have a way of identifying the elements of our set, which is through these numerals. We have a way of writing them down so that we can understand what we're talking about. We have a set of operations that we can do to the numerals. Namely, we can multiply and we can add, and we can do the inverses of multiplying and adding. So the inverse of multiplying is dividing or having a reciprocal. The inverse of adding is having a subtraction, negative numbers. Okay. The next thing that this talks about is factoring, like multiplication and division. What does it mean to multiply things, and what does it mean to divide things? So let's take a look briefly at that. The idea here is that any number can be constructed through a product of factors. So you pick a number, like 6. We can break 6 down into, whoops, there we go, yet again, here we go. We can break 6 down into a set of factors, 2 times 3. So these are multiplicative. That's what it means to be a factor, is that you multiply them together. You multiply factors, you add terms. So any two things that are being added together, so 2 plus 3, these are called terms. Any things that are being multiplied together are called factors. The way that we write things, we write expressions down in algebra, is going to be a series of terms. Each term is going to be composed of several factors, or one or more factors. Okay, so any number can be factored into a set of like smallest factors. These are prime factors. We haven't even talked, did we talk about prime numbers? yet in this book. I don't think it even talks about prime numbers. That's like a whole branch of mathematics, is the understanding how numbers relate to each other and what prime numbers are. So I guess we'll write this down. What is a prime number? So a prime number is a number that cannot be factored beyond itself and 1, beyond itself and the identity. So you pick a number, p, or like pick a number, let's say 4. 4 can be factored in a variety of ways. 1 times 4, or it can be factored into 2 times 2. Where 3, for example, can only be factored into 3 times 1. So these are what things can you multiply together to get the number that you're talking about. So this is called a composite number, and this is called a prime number. The way that I described this when I taught my kids how to do this stuff is, if a number is a prime number, then you can only make one type of rectangle out of it. So let me give you an example. With 4, you can make 2 different kinds of rectangles out of it. You can make a rectangle that looks like this, or you can make a rectangle, or you can rotate it so that it's this way. Those are the same thing. Okay, or you can make one that looks like this. A prime number is one that you can only make this kind of rectangle or this kind of rectangle out of. So, like, say 7. I shouldn't choose 7 because that's going to be a lot of stuff. Let's go with 5. Okay, so 5 is going to look something like this. And you can only make this kind of rectangle out of a 5. You can't make something like that. On the other hand, like 8, maybe not 8. Let's do 12. So there's a variety of ways you can do 12. You can do 1 times 12. Like this. You can do 12 like that. You can do 2 times 6. 2 times 6. You can do 3 times 4. Oh, that's ugly, but pretend that it works. So these are all the different ways that you can factor 12. Is 1 times 12, 2 times 6, 3 times 4. And so if you can have any of these kinds of factorizations, then it's composite. If you can only have this kind of factorization, then it's prime. That's another way of thinking about prime numbers. So one of the things that exists in algebra, or that's going to be an important concept in algebra, is that any number can be factored into a set of prime numbers. Okay, if you start with a prime number, then the factorization is 3 times that prime number times the identity. That's the only factorization that you have. Any other number is going to be factored into, let's say 72. 72 can be factored into a set of prime factors. So you can get a unique set. Doesn't necessarily, the order might, you can have a different order, but the number and the types of factors that you get are going to be unique. So 72 is going to be what? Like 3 times 24? 24 is going to be 3 times 3 times 2 times 2? No, is that right? 24 is 3 times 2 times 2 times 2. Right, 3 times 8 is 24. So the 72 is 3 times 3 times 2 times 2 times 2. And this is the only factorization that you can get of 72. There's no other combination of prime numbers that you can multiply together to get 72. So one thing that can be done with any number, with any digit, is that it can be broken down into these prime factors. And that's going to be a tool that will be useful as we go through the rest of the material in this book, is the ability to break down any number into its prime factors. Okay, so that gets us to this part, that we can multiply things together, we can divide them. You can write down an algorithm to work through the factorization. Okay, then there's these prime and the composite numbers. Right now, I'm not in a position to do something about number theory, but it might be fun at some point to talk about some of the weird things in number theory, which is basically the study of prime and composite numbers. This shows you the method that I used to factor things, except it used 48 instead of 72. So mine was cooler because I did 48. I mean, because I did 72. And it's unique. There's no other prime factorization. When you do mathematics in college, you don't just accept the fact that this is unique, you actually prove that it's unique. Okay, so another concept that's going to be useful is finding the least common multiple. What's the smallest, if I have two numbers, what's the smallest number that both of them are a divisor of? So let's say that I have 9 and 18? Well, that one's a little bit too easy. Let's say 9 and 6. 9 and 6. What is the least common multiple? What's the smallest number that can be divided by both 6 and 9? Turns out that it's 18, but how do I get to 18? So the answer there is that you break it into the prime factors, 3 times 3, and this one is 3 times 2. And the way that I learned how you do it is you write the first number down, you write down the full factorization of the first one, 3, 3, and then you write down the factorization of this one, and you line them up, 3, and I don't have a second 3, so I have to put it over here in its own column. So this is 9, and this is 6, like that. And then you take 1 from each column. So that's going to be 3 times 3 times 2, and that's going to give me 18. So you basically, anything that they share, any factor that they share, you only keep one copy of. Any factor that's unique to the numbers, you keep, you have to keep it, whatever that is. So this is, it might be, what about 9 times 6 times, or like 9, 6, what's the greatest common, or the least common multiple, the smallest number that 9, 6, and 5 go into? So you do the same thing, 3 times 3. Let's do 15. Okay, 3 times 3, 3 times 2, and then 3 times 5. So each one gets its own column. You take 1 from each of those columns, so I get a 3 times 3 times 2 times 5, and I should get 30. No, I don't get 30. 3 times 3 times 2 times 5 is 60. So 60 is the greatest common, or the least common multiple, the smallest number that each of these things can divide into. So that's a useful thing. What else is in this chapter? Working with, like, how do you manipulate numbers to bring about your nefarious purposes? All right, let's see how these things are actually organized so that we know what's going to be coming in the future, what's coming up ahead. We did the language of algebra. So we have our operations. Add and subtract integers, we know how to do that. Multiply and divide integers, we're going to pretend that we know how to do that. Add and subtract fractions. The real numbers we've basically talked about enough. Properties of real numbers we basically talked about enough. Systems of measurement, that's a physics concept. So we'll take a look at this one very briefly. Decimals, we kind of know how decimals work. So we'll do add and subtract fractions here. Why don't we do that next time? So we'll start with fractions next time, and then we'll move on to these linear equations and inequalities. So let's take a look very briefly at systems of measurements, and then we'll come back and do adding and subtracting, because fractions is something that often gets people confused. That's basically in 4th grade, it turns off half of the people that don't like math is because fractions are confusing. And so it's important that we understand what it is that we're doing when we're working with fractions. So let's take a look really briefly at this 110. Unit measurements. Okay, yeah, this is basically physics. So in this case, what is physics? Physics is essentially, you take the world that we observe and you need to map that world onto a mathematical structure. You need to map it onto a coordinate system. And the way that you do that is you define what your system of numbers looks like. So now your system of numbers means something. So where before you just have, here's a number 0 and 1, and when you're applying it to physics, you say, well, I want this 0 and 1 to represent some physical quantity that I observe in the universe, and so you assign a unit to it. So it could be meters, it could be eggs, it could be angles that rotate, it could be stars, it could be time, it could be mass. There's a whole bunch of things that now you're saying, I have these quantities that I know exist in the universe, and I need to map them onto some coordinate system. And I do that by assigning a unit to my number, and that tells me what my coordinate system represents. So a coordinate system being a number line. So now I have a number line. that looks like this. It's got, 0, 1, 2, 3. Here's my number line. It's all the real numbers. Maybe it's just the integers that apply, but some subset of the real numbers. And I'm going to claim that this thing has a unit associated with it, so it could be mass. And now when I describe or I use a number off of this line, it has a unit assigned to it. In this case, it would be kilograms, because that is the unit of measurement that we have in the metric system. And that connects me to the physical world that I observe. So I observe something in the physical world, I break it down into some unit that I quantify it in some unit, and I put that unit on a coordinate system or on a number line. So that's basically the connection between math and physics. Is math has all of these structures that are available to you. Mapping the world that you observe onto those structures is the physics. And then understanding the rules about how things change as they move around in this mathematical space is, that's like the laws of motion. So Newton's laws of motion describe how an object moves around in mass versus position versus time. So this will have units of meters, this will have units of seconds. So moving around in the meters, seconds, kilograms space is the rules about how you move an object around in that space. That's physics. Those are the laws of motion, for example. Let's see. So there will be problems in any textbook that deal with physical quantities that you measure and these unit systems. And so what that's actually doing is trying to connect math to the physical world, so that it's not like, when am I ever going to use this? You can see some applications in the physical world, but it's not really pure mathematics anymore. At that point, you're basically doing physics. All right, let me see if I can answer any questions that are here before we wrap up for the day. Let's see, what do we got? I'm having trouble wrapping my brains around what you're asking. Okay, so there's a question. You can also use the square root to say if a number is prime, or you can also use the square root to say if a number is prime or not. Really? I did not realize that you could do that. Never seen the rectangle idea. It's when you're dealing with a 6-year-old, that's something that they can understand. So I showed them with I think it was beans, like jelly beans. That's where I showed my kids what a prime number was. Let's see. I'm having trouble wrapping my brains around what you're asking. Maybe what helps me point out the weirdness of relativity, speed of light. Instead of the speed of light varying, the background space-time that varies. Okay, so this is a question about Einstein's theory of relativity. So here, the speed of light being a constant means that no matter what reference frame you're in, the speed of light will always move at the speed of light. So it's going to be the same regardless of the reference frame. So it doesn't matter how fast you're moving through space, the speed of light will always be, light will pass by you at the speed of light all the time. And that actually changes. Okay, so here's something that we can bring up that's relevant to the question that's asked, and also relevant to what we were talking about in terms of what addition is. So let's go back to addition. First of all, let me close this down real quick and open it back up so that it doesn't have this weird circle thing that I can never figure out. I have not yet taken the time to figure out what's going on with it. So we've seen addition already. We've seen multiplication and how they form a group. And there are a variety of ways that you can add things together. There's more than one kind of addition that still returns the group structure that we've seen. And I'll give you an example, a couple examples of this. It's kind of relevant to adding fractions. So eventually when we come back to adding fractions next time, we'll see this again. So if you want to add two numbers together, I'm going to claim that I'm going to invent a new binary operation called circle plus. So this is a new binary operation. It's like plus, but it's not quite the same as plus. It's a little bit different than plus. So I'm going to claim that circle plus also forms a group the same way that regular addition does over in this case, we're going to work with the real numbers. Okay, so the real numbers, I'm going to have this circle plus. This will also work on the rational numbers, but we're going to work with the real numbers instead of the rationals. I'm going to claim that if I add two numbers together, a plus b, a circle plus b, And this is going to be defined as, the way that you do circle plus is, instead of doing regular addition, you do this, a plus b. Now this is regular addition, and then 1 plus a times b. Okay, I claim that circle plus forms a group, that it's going to be commutative, and in this case it's going to be commutative. The reason it's going to be commutative is because both addition and multiplication are commutative, and so you can switch a and b in both of these things and you get the same result. So it's only commutative because these two operations are also commutative. It's commutative, it's associative, so that if you circle plus a bunch of things together, you do them one at a time. It's going to have inverse elements, which is going to be something that gets you back to 0. The inverse element is going to be minus the element, so a circle plus negative a is going to give me 0, and it has an identity. The identity is 0, so a circle plus 0 is going to be a. Okay, so it's got the same additive identity that addition has. It's got the same additive inverses that addition has, but it's got this weird kind of denominator thing. And I claim that this is a mathematical operation that takes me from any number less than 1 to any other number also less than 1. That this will always return a number that is less than 1 if my input numbers are less than 1. And the example that I give in my class is 0.9 plus circle plus 0.9. Okay, and so that would be 0.9 plus 0.9, like this is regular addition now on this side, and I've got 1 plus 0.9 times 0.9. Okay, so this is going to be equal to 1.8, the numerator is 1.8, and the denominator is 1.81. And 1.8 divided by 1.81 is less than 1. So I start with two numbers less than 1, I circle plus them together, and I get a third number that is less than 1. You can do this, you can convince yourself, using a calculator, that you will always get a number less than 1. This is, however, let me do one small change, and that is, if you have a number that is equal to 1, so if one of these two things is equal to 1, then you get that 1 back. So if I go a plus 1, a circle plus 1, so I follow the same rules, that's going to be equal to a plus 1 divided by 1 plus a times 1, and that's equal to 1. So circle plus has it has an identity. The identity is 0, but if you circle plus any number less than 1 with 1, you get 1 in the end. This is the way that you add in actual space-time. So the space that we inhabit, the universe that we live in, this is the way that you add velocities. You add velocities using circle plus instead of regular plus. And the speed of light, in this case, is equal to 1. Okay, so when you add velocities that are less than 1, it's going to be a fraction of the speed of light. If anything that you add to that system is equal to the speed of light, it returns the speed of light. That means the speed of light is always going to be constant. No matter how fast you're moving relative to it, if you add the speed of light to it, you always get the speed of light back. Where if you add anything less than the speed of light to it, you'll always get a number less than the speed of light back. So that is a binary operation acting on integer or on real numbers between 0 and 1 that has all these properties, including the unusual property that when you add 1, you get 1 back, which is pretty gnarly. So that's a different kinds of addition is something that we come across quite a bit. So for example, I can show you two different ways of adding pairs of numbers. So let's say that I have two pairs of numbers, A, B, and I'm going to add to them C and D. And this is, I have some quantity called addition or some operation called addition, and I'm going to add these two things together. A plus C, A plus C, and B plus D. Okay, so this is one way that I can add these two numbers together, and it's going to have the same properties of what I described before. It's associative, it's got inverses, it's got an additive inverse. In this case, it's commutative. So this forms this algebraic structure with this binary operation, except now you're working on, your sets are actually pairs of numbers instead of individual numbers. And I'm going to complain, or I'm not going to complain, I'm going to convince you, hopefully, that I can have a different kind of addition that also satisfies the same properties. It's also associative, it's also commutative. Is it commutative? It's also, yeah, it's commutative. It has inverses, it's got everything that you want for a group, but this one is going to look like this: AD plus BC, BD. That is, so this is a different kind of addition. So here's one type of addition for pairs of numbers that looks like this, and this is a different type of addition for pairs of numbers, and it looks like that. And it's got all the fantastic properties that we love about addition and multiplication. Okay, this is the way that you, this top one is the way that you add ordered pairs. So if you have XY coordinates, you're going to add, you know, ZW to it, and you're going to get, you add the X coordinates together because they're on one number line, and you add the Y coordinates together because they're on a different number line, and you're going to get this. So you add the X coordinates, you add the Y coordinates, and you get another pair of numbers that is within your space. In this case, it's some two-dimensional space on a coordinate system, which we haven't really covered yet in this class, but, or in this series of lectures, but we'll get to it. This we will touch on next time. This is how you add fractions. When you add fractions together, you have to find the common denominator. So the common denominator is the product of the existing denominators. So this is like the numerator and the denominator, and this is the numerator and denominator. And this is how you add fractions together. And when you add fractions together, you're going to find that it's associative, it's commutative, all the wonderful properties that we expect. So these are two completely different ways of adding pairs of numbers together, and they have they satisfy the same mathematical requirements of groups. The same mathematical requirements as addition, as multiplication, as rotations of a sphere. All those things are all satisfied. So when someone talks about relativity and the fact that you can never travel faster than the speed of light, it's because when there's a different kind of addition that's associated with motion through space. Like the real kind of addition that's associated with motion through space is the one where when you add the speed of light to it, you get the speed of light back out. And so you can never travel faster than the speed of light. Have I ever considered that space of units is a vector space where the number of unit multiplication that is the addition of the vector space? Where the number with unit multiplication is the addition of that vector space. Maybe I have. I can't picture that off the bat. Let's see, two direction speed is the same. What about one direction, Professor? When you have a direction, it's the same. So that formula that I gave with velocity addition, it doesn't matter if you're moving to the right or the left. And you would you break it into components corresponding to each direction. So in physics, you will have a parameter space, and that parameter space is going to consist of axes, and those axes are going to have units. They don't have to have the same unit. You can have an axis that's mass, you can have an axis that's time, and you can have an axis that's space. And you can have a system that evolves in this parameter space. You can also have a parameter space where everything has units of length. So you can have an x direction, a z direction, and a y direction. So now all these things have the same unit. They're all measured in meters. And then you can have motion through some three-dimensional space. But it doesn't have to be, they don't have to share the same direction because the coordinate axes of those two things are independent of each other. So movement in this direction does not necessarily imply movement in this direction. They can be independent. So it's pretty common to have, position and time on a plot. And so now you have a two-dimensional parameter space. One direction corresponds to one quantity that you can observe in the universe, and the other direction corresponds to a different quantity that you can observe. And then you look at the motion of some particle through that space. The textbook I'm working off of is OpenStax. OpenStax. And we are looking specifically at the elementary algebra, second edition elementary algebra. It's a free textbook. You can download the PDF offline or off the internet all by yourself, and they've got all sorts of subjects. Let's see. How do I add meters per second to a 1? Oh, so yeah, it's in that case it's this fraction of the speed of light. So the numbers that you're adding is a fraction of the speed of light for the case of those Lorentz transformations. Or is it a Lorentz transformation? It's a velocity addition formula. Let's see. All right, so that's what I've got for today. Next time we will be doing, we'll pick up with addition of fractions, like how to do that and what it actually implies when you're doing something like that. So that should be pretty cool. Fraction addition, thank you for that sub, King's Throne. Let's see, can axes be abstract data, abstract algebra? So the axes on any physical, like anything, they don't even have to be pure units. So in the SI unit of, in the International System of Units, there are, is it eight units? What are the units? So there's time, there's distance, so length, there's mass, there's candela, which is a derived unit, there's a unit of electric current, so the amp, there's a unit of, let's look it up real quick. Some of them are fake units. So some of the SI units are not real units. They're conversions that get you from cool sciences to crappy sciences. Units that get you from physics into chemistry. So Avogadro's number, for example, gets you from physics into chemistry. So this is the system of units. The SI system of units changed recently. The definitions changed. Here's the... I have several videos, I think, on the change in the SI system of units, like how they redefine things. You have to dig through my YouTube channel to do it, to look at it. So mass, seconds, kilograms, those are the primary units. The amp is electric charge, how much electric charge moves by per second. And so you can see that it actually depends upon the seconds. So these are fundamental units, and they go into some of the other units that we get. So temperature is related to mass and kilograms, and Boltzmann's constant gives you the temperature scale. That again is not a temperature is not really a fundamental unit, because it's a statement of the average properties of some system with a thermalized distribution, Maxwell-Boltzmann distribution of stuff. The candela is a unit of power, which is a derived unit. It's power per square meter observed in the band where the eye operates. So it's a little goofy. Avogadro's number is like a dozen. Like, is a dozen a unit? No, it's not really a unit. So the most fundamental units are these ones, but then you have other conserved quantities that you have to deal with, that you have to contend with, and in particular electric charge. So you get the amp from that. Okay, let's see. Average, the definition of temperature is kind of whack too, following, allowing there to be negative Kelvin. Well, so I don't think you can have negative Kelvin. You can have negative heat capacity, but I don't think that the, because there's square numbers in there, right? You have to get meters per second squared, and so that takes any negativeness out of it. So, but there are issues where you can construct something with a negative heat capacity, which is a little weird. So I think did somebody win the Nobel Prize for that? When you have the spin states and then you flip with the magnetic field, and now all the spin states are opposite of where they should be, and so you get a negative heat, like it actually gives up energy in order to come into equilibrium. So the question about the magnetic field and magnetic poles, there's no size. So there's no magnetic monopole. There's no infinitesimal magnetic north pole. It always comes as a north and south pair. Convert 1 units of C to convert to the other units of meters per second. Let's see. Oh yeah, okay, so there are a variety of different definitions that might apply in certain circumstances, but the fundamental definition I don't think allows you to have negative temperature. Do electrons have 2 poles? They don't have 2 poles, but they do have a spin. So electrons, while they don't have 2 poles, because of the spin you have an axis, and the axis has a positive and a negative direction. And so that's a difference. So when you say that something has a location, now this doesn't work. So we'll just go with what I was saying earlier, and that is that a single electron might have a location, in which case it can be a single particle, but the spin of that electron is a direction, and the direction can have a positive. Now it's a line, and so you have a positive and a negative direction. And so the same kind of thing is basically what's going on with a magnetic field, is that it corresponds to some kind of angular momentum. This is the angular momentum in the electromagnetic field. There's some technical aspects of it that I can't pull off the top of my head, but it is associated to some extent with spin. And so then you have, because of the spin, now it's a direction instead of a single point, and so you can get a positive and negative value. And there's always a positive direction and a negative direction when you have a line in that kind of space. So particles moving faster than c. So Cherenkov radiation is particles moving faster than c divided by the index of refraction, not faster than c. And so that matters.